Arjun bhai, if you check like whether you are the host now. Yes, Arjun bhai, you are the host now. So yes, sir. Maybe you can.
Now it is showing.
Yes, sir.
Yes.
We can see your screen, sir.
My screen is visible.
Yes, sir. We can see your screen.
Yeah. So this is the preview of how the BLDC motor practically looks like and what is actual construction inside. BLDC motors are widely used in industries, electric vehicles, uh, pumping and air compressors. Modern due to its high efficiency, high power density, and high efficiency at higher speed and higher torque, and better control facility. Uh, so we have, if we look on the scenario of the motors in industries, so in industries here lots of sectors: material processing, material handling, refrigeration, fans, and air compressors. So different proportions of the motors are used in industries. So various standards are there which define the methods for determining the efficiency, which provides the minimum mandatory efficiency from no load to full load, and different uh, standards which introduce super premium efficiency. So it will ultimately result into the energy wastage and reduction in the energy wastage and annual energy saving, and it will uh, ensure the environmental safety. We can see that here that as per the third norm IE3, we have above say 95% of efficiency are higher than 100 kilowatt motors. Similarly, other standard uh, institutions are there which define the efficiencies for the motors. So there are also various power quality issues in the uh, motors. So there are various standards which deal with the power quality and harmonics. They also IE standard 519 deals with the 1992 deals with the THD level. So THD level is basically defined 3% for hospitals and airports and very sophisticated controls, and 5% in general system, and 10% are dedicated systems where the loads are present. So we all of we desire only for the less than 3% of THD in the BLDC motor system operated with the AC to DC system. Here we have some of the outlines of the speed ranges of the BLDC motors. Here we can see that 2,40,000 RPM is the speed given in the reference 18, which is considered as high speed. And so various literatures have shown different ranges of speed as low, medium, and high. Some literatures have said the same speed as medium speed. Some literature have said the same speed as low speed. So overall, we have different speed ranges, and up to now we have 94% of 94.6% of maximum efficiency recorded for BLDC motor, and as far as we are dealing with the uh, capacity of motor, 20 kilowatt electric car motor has been till now in the market, and this is to be noted that 15% of uh, BLDC motor has 15% more power density than conventional PMSM. So we have various applications of BLDC motor like domestic purposes, electric vehicles, automotive robots and robotic manipulators, high-speed processing and manufacturing, submersible pumps, hard disks, and ultrasonic motors. These very super efficient motors are only can be used here in this system. We have also the applications of BLDC motor are the very precise controls in the medical field, in the radiation therapy, diagnosing and testing equipments, dialyzer. Similarly, we have a emerging field which is now taking a wide research area, that is electric vehicle, and the BLDC motors are mostly used in electric vehicles due to their fast response and higher dynamic capacity, higher uh, torque to weight ratio, higher power density, and better control facility. So other applications are also here. We can see the conventional PMSM and BLDC motor bindings have some difference. We can see here that the bindings of phase A, phase B, and phase C have half of the part above and half of the part downside. Phase B is 120 degree with the axis of phase A, and similar in this PMSM, we have distributed winding, and there are some certain phase belts which are at certain phase belts are at up to certain limit of special angle, and the windings are overlap. Here, no winding is overlap. Only at the same slot, the other windings conductors are also incorporated. So here we see how the BLDC motor is basically controlled. The most basic control of the BLDC motor is using the Hall sensor, because in conventional DC motors, the mechanical movement itself changes the terminals of binding. But here, whenever there is a rotation of the magnet, we have no any method to sense the position and energize the appropriate bindings, which will provide the proper torque. So using this Hall sensor, we can determine the position of the rotor, and then we can energize the uh, proper uh, proper phase or appropriate rotation. And we have positive side sequence and negative side sequence. In the positive and clockwise and anti-clockwise, we follow the different commutation algorithms using the Hall sensor. So in the BLDC motors, we have simply the six switch leg, 3 leg inverter, which can be comprised of MOSFETs, IGBTs, or simply the transistors. And nowadays, the high speed and super efficient high capacity machines are made up with the gallium nitride and germanium SiC, silicon carbide, and gallium nitride superconductors and semiconductors. Here we have the DC link in this system. We can see in this system we have the DC link also. We can provide the supply, and we can provide the supply from the renewable energy source. We can supply the power from the DC storage like battery and supercapacitors. We can provide the higher or lower power from the bidirectional DC-DC converters. If the DC storage is at lower voltage, we provide the boost converter and buck converter, the DC side, DC battery side. So we have this complete system of the BLDC motor. This is closed loop where we can control the DC-DC converter, or we can control the commutation logic. In current control method, we control the inverter current. In the voltage control method, we control the DC-DC converter voltage. So we have also the various sensorless methods. So sensorless methods are flexible. We can change the response of the motor and the minimize the current at high speeds as compared to the conventional sensor based schemes. So we have also the voltage measurement facility in the DC converter stage, and if we are using the AC to DC converters in the stable systems, we can use the PFC correction method. So this is the simply the modeling, and we will not go more into the modeling. We have simple diagram of this motor. From here, we can understand how the Hall sensors are placed and what is the range of the Hall sensors. Here, Hall sensor A is placed at the axis of phase A. That is here, where my arrow is mouse arrow. Here Hall sensor had the center. So its range is from -90 to +90. We are assuming the phase A axis as 0 degree. Similarly, the Hall sensor B is placed at the center of phase B, and its range is the 30 degree from the phase A up to 210 degree from the phase A. Okay. Similarly, we have another Hall sensor. This is a IC which has some voltage provided and it gives the output voltage. So this Hall sensor chip is placed in the stator below the C phase winding. So its range will be 150 degree starting from the phase A axis. So from phase A axis, we measure 150. So here it will start, HC will start, and its range will be 330. So we have the Hall sensors placed, and according to these Hall sensor positions, we have.
एक मिनट वो पढ़ा रहे हैं यार.
So here we have the Hall sensor signals, that is 100, and now I will illustrate you how this table be defined. So for this table, I would like to come to the Zoom board. Here we have phase A, phase B, and phase C, and this is phase B negative. Is it visual?
Yes, sir.
And here we can see C minus. C minus means when we give the negative terminal, we connect the phase A to negative, then A minus, A negative. Okay, and then we connect the phase C to positive, it will be C plus. Similarly, all other terminals. So here we can see that we have this star connection in the BLDC motor, A plus, B plus, and C plus. We can also say C1, C2, B1, B2, A1, and A2. So A1, A2, and A2, B2, C2 are connected together to make the start point, and we have in every terminal there is one DC source and there is one switch, VDC plus minus in every terminal of the phase, this VDC and plus minus. Here in other terminal we have is BDC positive and negative. The BDC terminal is common. All the BDC terminals are at the same place, making the three-leg inverter. We say here H1, L1, phase B, which is upper switch is high switch and low switch L2. We say third phase S3 and L3. Okay, so according to the positions of the rotor, we can sense the we can energize the appropriate phases. Suppose our rotor is here, then we will have to energize such that our axis of the flux goes here. Okay, so we will energize A plus C minus when the rotor is at this place. So for this, we have to know how the Hall sensor logics are varying. So here we have another page and simply okay. So this is the stator. We are defining this circle by as a stator, and here we have the HA, that is Hall sensor A. Here HB and here HC. It is placed under the core and it is pasted. This IC is pasted and we provide the external supply to this IC. Please increase the meeting time. Okay, so here the range of the center of the phase A is phase A axis and the center of HA, and this one is total minus 90 degree, and this is 0 degree. This is 90 degree, and this is 270 degree. Sorry. 150 and 270. Okay, is it visible?
Yes, sir.
So similarly, we have another Hall sensor. We have and we will take okay. So remaining part is
ये बंदर है वहाँ आजा लगा देखा तो
okay. So we have phase B. Which one is please mute the voice. Please mute the voice. So here we have sensor, third Hall sensor signal. So,
अरे यार कहाँ पहुँचा
Sir, someone is obstructing the meeting, sir. Hello.
Yes, sir. I have seen he's not present here right now. So, sir,
Yeah.
will we start a new meeting? Like it's 5 minutes left. After 2 or 3 minutes, again we will rejoin, sir. You can continue.
Yeah. I'm starting. Just minutes.
आ रहा है क्या बोले आया बोले
अभी कनेक्ट है क्या कहीं पर? Please allow me the sharing. If any
Azim
person
bhai, Azim,
and
Azim bhai, you are the host now.
please remove him and block. Hello. If any person
Sir,
please
yes, sir. You are the host now, sir.
yeah.
Sir, you are the host now, sir.
Okay, now I'm sharing now. So here till now it's okay. Okay, so here we have another Hall sensor signal. I will have to drag it. First, I will draw the sectors here. We have 60 degree, three sectors are there, and six sectors are there. So in these only sectors will be the Hall sensors. Okay, so second Hall sensor signal will be here, and third Hall sensor signal will be this one, and this one. Okay, so this is total 360 degree. Here every Hall sensor has 120 degree displacement from each other. Here this is Hall sensor B. This is center of Hall sensor C and AC. This is phase B center. Okay, so here we see here we have 1, 0 and 1. Here we have the Hall sensor signal 1, 0 and 1. Here exactly after the completion of this rotation, this Hall sensor becomes 1 here. 1. And here is 0. And this is 0. Okay. So exactly when the rotor reaches here, this is phase B position, and exactly when the rotor reaches this position, the Hall sensor signal becomes 100. So the phase we should start is A plus and C minus. Then the overall flux will be here and the rotor is actually here. Is it visible? Can you hear, please? Please respond me.
Yes, sir.
Yes, sir. Sir,
Okay.
you are audible.
Yeah. So this is Hall sensor and this is the phases. This is phase B. A minus, B plus here. This is C plus, and here B minus. Sometimes
Sir,
the
sorry
Hall
for the interruption. Sir,
Yes,
sorry for the interruption. We have only 15 seconds left. So, everyone who are the participant, you have to rejoin again.
I have to
Sir,
rejoin.
yes, sir. We are rejoining.